While Detroit is writing multi-billion-dollar checks to cover its EV mistakes, a factory in Wuxi just quietly unveiled a 75-kilogram silver box that makes almost every American electric motor look outdated. No press conference chaos, no Elon-style hype cycle, just a number, 93.8% drive efficiency. That's the highest ever recorded on a mass-produced electric drivetrain, and right now, Tesla, Ford, and Volkswagen don't have anything that matches it. Here's why that single number matters more than it sounds like it should. This isn't about squeezing out an extra 20 miles of range. It's about a manufacturing shift that's already reshaping who can build a cheap EV and who can't. And it's happening while Western automakers are still cleaning up after their own EV bets went wrong. Stick around because by the end of this video, you'll understand exactly why this boring efficiency number has engineers in Detroit a lot more nervous than they're letting on. If you want to stay ahead of where the EV industry is actually heading, hit subscribe before we get into it. Real numbers behind 93.8%. Let's start with what that efficiency number actually means, because 93.8% on its own doesn't tell you much. Think of an EV's drivetrain like a pipe carrying water from your battery to your wheels. In a perfect world, every drop makes it through. In reality, every connector, every conversion step, every meter of wiring leaks a little energy out as heat. The fewer leaks in the pipe, the more of your battery's energy actually turns into forward motion. For years, the best Western EVs have lived in a fairly tight band. Independent estimates commonly put a Tesla Model S Plaid's drivetrain in the low 90s, with the BMW iX landing a bit behind that, the Volkswagen ID.4 further back still, and a heavier vehicle like the Ford F-150 Lightning trailing the pack. None of these are official published specs. They're informed estimates from engineers who've torn these systems apart, but they give you a realistic picture of where the current bar sits and why closing even a couple more points has proven so difficult industry-wide. That's what makes this next number worth paying attention to. Geely's new drive system, built by its subsidiary Infimotion at a plant in Wuxi, was unveiled in mid-July and rated at 93.8% under China's CLTC cycle. Geely internally calls it the Thunder 16-in-1 Intelligent eDrive, and it's set to debut on the Geely TT, a new electric sedan under the company's Galaxy sub-brand. And yes, before you get too excited, there's an asterisk. CLTC is China's own testing standard, and it's known to be more forgiving than the EPA cycle used in the US or the WLTP cycle used in Europe. Western engineers have pointed out that CLTC numbers can run 8 to 10% optimistic compared to real-world EPA conditions, so skepticism here is fair. But do the math anyway. Even if you knock this system down by that full margin, landing somewhere around 85 to 87% under a harsher EPA-style test, it's still competitive with or ahead of what legacy automakers are putting on the road today. Adjust for the skepticism, and the headline claim still holds up. Inside the 16-in-1 powertrain. So how did Geely get there? Not through some breakthrough motor material, through addition by subtraction. Most modern EVs scatter their electronics across the chassis: the motor controller, the onboard charger, the DC-to-DC converter, the thermal management system. These typically live as roughly a dozen separate components wired together across the vehicle. Every one of those connections is a place where energy leaks out and a place where something can eventually fail. Geely's new system, internally called Thunder, takes 12 of those hardware components and fuses them into a single magnesium alloy housing alongside 4 software layers handling things like intelligent energy management and health monitoring. 16 functions, 1 physical unit. The engineering numbers back up why this matters. Geely says the redesign eliminates more than 180 individual components compared to a conventional setup. High-voltage wiring drops by 30%, low-voltage wiring drops by 15%, and the whole unit weighs 75 kilograms, lighter than comparable systems on the market today. Every one of those 180 deleted components was a potential failure point, a connector that could corrode, a joint that could loosen, a warranty claim waiting to happen 5 years down the road. Fewer parts doesn't just mean lower weight, it means fewer things that can go wrong once the car is in a customer's driveway, and fewer line items for a service department to worry about. And this isn't a low-power science project built purely for a headline number. The system comes in 2 configurations, a single-motor version producing 245 kilowatts and a dual-motor all-wheel drive version pushing 425 kilowatts, that's 570 horsepower, enough to get a Geely TT sedan from 0 to 100 kilometers per hour in 3.8 seconds. It runs on an 800-volt architecture for fast charging. Now, the 2 pieces of engineering that make sustained performance like that possible, and this is where the design gets genuinely clever. First, thermal. Cram 16 functions into one 75-kilogram housing, and you've also crammed all their waste heat into one small space, less surface area, less airflow to dump it. Geely's fix is 54-channel directional cooling. Instead of one coolant loop wrapping the outside of the housing, coolant runs through 54 internal channels, each aimed at a specific hotspot: stator windings, inverter electronics, gear mesh, rather than cooling the box as a whole and hoping heat finds its way out. Geely says this cuts peak motor temperature by up to 15 degrees Celsius, which matters because both efficiency and lifespan degrade as temperature climbs. A system running 15 degrees cooler stays closer to its peak efficiency for longer instead of throttling back. Active lubrication on the shaft and gears handles the mechanical heat, too. Second, durability. Geely is engineering the system to a 5 million kilometer service life target, validated at the component, assembly, and full vehicle level. For scale, a car driven 20,000 kilometers a year would take 250 years to hit that number. This is a fleet-level bench and accelerated life testing target, not a real-world mileage claim. But publishing it signals confidence that fewer components means fewer failure points. And here's why competitors can't just copy this fast. It's manufacturing physics, not a secret formula. That magnesium housing isn't bolted together. It's die-cast as one large structurally integrated shell, and magnesium is harder to work with than aluminum. It's more reactive, more prone to porosity defects, and it demands tight control of temperature and pressure to avoid cracks in a part this large. Getting that casting right at production scale typically takes years of tooling investment, and you still have to route 54 precision channels through it and validate the whole thermal system together. Large format magnesium casting, plus internal channel routing, plus multi-year durability validation isn't something Detroit retools for in a single product cycle. Geely backed the whole thing up with real-world stress tests too, not just lab numbers. A Qinghai Lake efficiency run logged just 8.20 kilowatt-hours per 100 kilometers, setting a Guinness World Record for the lowest energy consumption by a mass-produced battery-electric sedan on that route. And in a separate torture test, 2 Geely TT sedans performed a continuous, synchronized 46-kilometer twin-vehicle drift on a wet surface, a stress test on torque control, thermal management, and power delivery that a spec sheet alone can't fake. That earned a second Guinness title. 2 very different tests, both pointing at the same conclusion: the efficiency number isn't just a lab trick.
Why Detroit is bleeding billions. Here's the part that should actually worry American automakers, and it has almost nothing to do with the efficiency number itself. Deleting 180 components doesn't just make a car lighter, it slashes the bill of materials, it shrinks the supply chain, it reduces the factory floor space and the labor hours needed to assemble each vehicle. Every part you remove from the drivetrain is a part you don't have to source, inspect, wire, and warranty. Compare that to where GM and Ford currently sit. GM has taken roughly $6 to $7 billion in charges tied to unwinding its EV strategy. Ford absorbed a $19.5 billion write-down and discontinued the F-150 Lightning entirely, the kind of move a company makes when the math on a product stops working. Stellantis took the largest hit of all, over $26 billion. Honda cut its planned electrification and software investment by roughly 30% through 2030, directing the money toward hybrids it can sell today. Industry-wide, write-downs and losses now total somewhere around $55 billion as automakers walk back an all-electric bet that overshot demand. Meanwhile, a Chinese automaker just found a way to make EVs cheaper to build, not more expensive. That's not a small gap. That's two industries moving in opposite directions at the same time. Lower production costs translate directly into pricing power, a manufacturer spending less per vehicle on parts, wiring, and assembly labor can price aggressively and still protect margins, a position Western automakers, weighed down by billions in restructuring charges, simply aren't in right now.
The global battle for cheap EVs. Which brings us to the part of this story that doesn't get talked about enough. This fight isn't happening in the US. Picture a fleet manager in a market without steep import tariffs on Chinese vehicles, somewhere across Latin America, Africa, or Southeast Asia. They're not choosing between a Tesla and a Geely on brand loyalty. They're comparing sticker price, running cost, and warranty history across dozens of vehicles at once. When one option is cheaper to build, cheaper to maintain, and backed by fewer parts, that decision gets easy, fast, and it's made at scale. U.S. tariffs on Chinese EVs protect domestic sales inside American borders. That's real, and it matters for now, especially for manufacturers and workers depending on that protection while the industry resets. But protection inside one market doesn't slow the technology down everywhere else. While American automakers spend 2026 absorbing write-downs, Chinese manufacturers are exporting integrated lower-cost drivetrains into exactly the markets where tariffs don't apply, markets that represent the majority of future EV buyers globally, where price sensitivity decides who wins. There's a slower-moving consequence, too, for anyone who already owns an EV built on the old scattered architecture. As integrated lower-cost powertrains become the standard, older generation EVs risk losing resale value faster than buyers expect, not because they stop working, but because the platform underneath them is aging out. So where does that leave the average car buyer today? If you're shopping for an EV in a market where tariffs keep this technology off the table, that protection buys you some breathing room, but it's worth knowing it's happening and worth watching how quickly it closes the gap once it arrives. If you're shopping in a market without that shield, the calculation changes today, not 5 years from now. That's the real story behind 93.8%. It was never just an efficiency number. It's a preview of who gets to set the price of the next generation of electric vehicles, and it's not who you'd expect. So here's the question worth sitting with. Should governments keep protecting domestic automakers with tariffs, even if it means falling behind on the engineering itself? Or should the industry be forced to compete on cost and efficiency right now, no shield included? Drop your take in the comments. I read every one of them. And if you want to see exactly how Toyota is answering this same threat with a completely different bet on solid-state batteries instead of integrated drivetrains, that video's coming up next, and it's a very different strategy. Subscribe so you don't miss it.